Hello, everyone. I'd like to go over Modelsim uh, example, and we would like to talk about how a simulation can be done on Modelsim in a very instructive manner. We'll go through an example. In order to run Modelsim, we need some privileges in subdirectories. So in order to do that, we have to supply that to Modelsim. Just go down to C, that's your directory, and from here find the Intel FPGA installation directory. Here, what you can do is you can run cacls command as shown on the screen. Backslash t, that's the directory, backslash t, backslash p. The username, column F, gives the privileges for write purposes in that directory. So you better do that. It asks you for confirmation, and then you process all these files as a writable location. So that when that finishes, you can open up the installed Modelsim following that. So you just got to start that once it finishes. I had already done that before this session, so I can easily run Modelsim without any problems, hopefully. So it just starts up. As you see, we have the Modelsim simulation program has started with a welcoming screen at the start. We just close that, and then we proceed with opening up a new project. That's your first step. So you come here and you open up a new project. It warns you that it's going to stop the current project and it's going to go on with a new project. At this point, you should give a project name here. That would be named as a top entity of your design. So make sure that that's your top entity in your project. I would name it um, anything I like, counter uh, example or counter X, maybe my project name. And this everything goes down here into the default library location that's under work. So in this subdirectory of Intel FPGA slash the version of Modelsim slash the work directory is going to contain the compiled information for my project. And I just click OK here. At this moment, you have to decide if you're going to create a new file or add an existing file into your project. For simplicity, I would like to just add an existing file into my design. So I click on this and search for the project that I would like to add to my design. I just created a file called counter 2023 VHD earlier. That was already there. So I picked it up for my simulation. I just clicked OK. Now, at this moment, we're just going to click OK and then go on with our simulation. Now, this file is already in this project window, as you see here. We have several windows. Some of them are project windows, some of them are library windows, as you see on the screen. That includes the library contents are going to go into this location as well. So we have the project file is already in this location. So what we have to do is we have to start up compilation of this and um, form the compiled version of this by saying simulate here. So what we're going to do is we're going to compile it by compiling all, and as you see, it just compiled here and it says the compilation is successful. And down here, there is a transcript window. You can actually relocate these windows to anywhere you like on the screen. So you can just move them around like that. Okay. You can move it down here as a block. It goes down here as a block. You can put it aside, or you can just click on this icon that you see um, somewhere on this, so that you can dock or undock. For instance, you just don't want it at this location. You just click on it, it goes somewhere else on the screen. So you have to carry, you can carry it around, and then you can put it back by saying dock it back to the location that you have found. So it goes back to the location that you wanted. So you have this counter VHD and it's already compiled. Now what you have to do is you have to just simulate it and start the simulation of that. As you see, when you say start simulation, you have the screen that is designated to search, allows you to search for your design, comes up, and then from here you can just look around and then select your entity plus the architecture that is associated with that. Okay, so that is your entity plus the architecture. There's also a benchmark that has been compiled already in that location, but we're not interested in that. We just click on the architecture or the entity that's going to correspond to our simulation. So we click on OK. That's going to load up on our screen in a second. With all the content that is available for us, that is necessary for us to simulate our design. Now, as you see, you can see the signals that are underneath your architecture here in this location. So you have all those signals in your design with all these details up to the bit level. Then you can move those into the simulation window and you can run your own simulation from this. So what you can do is, you can do either two things. You can just click on them and then you can move them into this window individually. Or what you can do is, you can add to the waveform. This is the waveform window over here on the right hand side. You can put the waveforms signals in the design into the waveform window. So what happens here, these design signals, actually they are the inputs to our design, are carried into our in the entity into our waveform window, as you see here. So at this moment, what you can do is they are initialized to 0 at the beginning. Of course, you can force them to become different values. So you can click on, play around with these values. You can click on counter clock, for instance. You can make the clock, you can define this clock by right-clicking on that. And then you can change those values in terms of clock. So with a duty cycle of 50, we have a period of 100. That means we have even duration for zeros and ones. The first edge happens to be a rising edge. We have the high values and low values defined. All right. So let's move on. We just click OK from here, and then we come here, and then we just form a clock signal for this design. And you can also reach your your file that goes along with this counter design. Okay, so what you have to do is you have to come to that, and then you have to double click on that to find that file in your window over here. Okay, let me just enlarge it on the screen to make sure that it is seen. Yeah, we have a library tab here, as you see on the left hand side, and we have the project tab that happens to contain our VHD file. As you see, we have different colors of how the VHD file is written. You can actually click on any of these red uh, identifiers to see what is going on inside of them at any time during the execution of your simulation. You can reach those contents as you like. What else would I be needing to run this execution? So for fun, I just start out the simulation by running step by step. Now there are some shortcuts as you see on the screen. You can just position them as you like, as you're liking. The most important one is your simulation and how long you're going to run. The first step is to run maybe for 100 picosecond and see how that works. So as you see, when I do that, it runs 400 picoseconds and shows me how the counter is run. And this design actually includes functionality to increment the counter step by step. So at each iteration of the clock, the counter actually, as you see the design, counter is incremented. So the clock event and the clock is equal to 1 means at every rising edge, I have a flip-flop that's going to actually increment this counter. So the increment count basically refers to this function, as you see on the screen, and it just increments the counter by 1. There's also an asynchronous reset, as you see here, that actually resets the design upon receival of a reset is equal to 1. So when reset is equal to 1, then your counter becomes a 0 at any time, regardless of the clock operation. That means that's an asynchronous clock operation. Okay, now we have that information. We can run the simulation for as many times as we like. So we can simulate it through this button over here. So we can run the simulation as much as we want and see how that actually progresses, how the counter actually progresses through time as we move the clock from time to time. Okay, so as you see, how the counter is incremented as a result. Okay, while we do that, actually we can in real time check out the contents of the counter. So we can come here and then we can click on it. We can right click on it and we can see the contents of that counter by um, clicking on the examine here and see what the contents are going to be for that count value. So that happens to be 0000. That's a 4 actually, right? So the next iteration is going to be 5. Now there is one more thing that I can move. I can step into this code. I can you have my pointer on the left hand side over here. I can step into this code and I can watch the HDL actually step-by-step processes my execution. So I can step into that, as you see. So as you receive a clock, you come back to this same point again at some point in time. So once you do that, this is that moment. Count is now incremented again to become 5. It doesn't happen immediately. Of course, it has to go through this function. You progress through this function. And then when you return from this function, the counter becomes incremented as you try to check out the content through examine once again. So that becomes, we probably have incremented twice here. So that becomes 110, 4, 5, 6, and so forth. Now you can double check that value has changed by checking in how that changed through time. So that becomes a 5, that becomes a 6 at this moment. Probably we might have missed 5 along the way when the counter has changed. when the clock has changed. Sorry. Okay, so we are fine with that. What we can do, we can actually modify other values such as reset at this moment. So why don't we do that? Let's force this signal to be equal to 1. So when this is equal to 1, after a certain amount of delay, that would be nice because we don't want that to occur immediately when the signal changes. So we would like some sort of a picosecond of delay action to be occurring. So we proceed again by simulating another 100 picoseconds this time. So we see that the simulation at this moment, after 20 picoseconds, have turned out to be a 1 right there. By the way, you can zoom in into this waveform to see in more detail. So I can see that reset is high. That makes all these signals equal to 0 at this time. So I just changed manually all these signals. I just forced them to become a 0. Right? Once you do that. Okay, you can take back the reset once again. Let me back up, and then you can put reset back to. So no matter how many times you change your clock, as you see here, let's run our simulation more. As you see, the counter is not going to change its contents. Since there's no content changing, actually there's no value written onto the top of the program, of the waveform, right? So let's try to, from this point on, the last moment, we can change reset back to 0. I can change that back to 0. I can expect now the counter back to its regular simulation to be activated. So as you see, we started having some signal changes on the counter as well. So that was a summary. Thanks for listening. That was just a review of what can be done about the simulation, how we can see how the design actually works, how we can trace it through our HDL code as well. We can just monitor how the execution can be debugged. If there are any problems in your code or something like that, you can also check on those operations as well. When I double click of it, of course, it gives me a larger overview of how this design is seen by the compiler. It's not going to be a fully synthesized version of that. We haven't really synthesized it, of course, but it just gives me an overview of how this design actually looks from the side of the simulation. Okay, thanks for listening. See you back at the class. Take care. Bye bye.